Thank you, Lee, for the introduction, and good afternoon, everyone. So today I'm going to talk about our work on fiber-based electronics, and particularly the world of using fiber-based devices for e-textiles, looking at sustainable directions for these new emerging technology. And so what we do is strongly motivated by the fact that wearables in general are being forecasted or becoming a very, very popular and widespread technology. Forecast says that, as of the beginning of 2019, so last year, the total revenues around wearables are really soaring up to, with a rate of 23%. And that really means that this is going to be becoming a very widespread and popular technology in the future. And this is mostly given by the fact that areas that normally tend to be skeptical with new innovative technologies at the beginning because of reliability issues, other things, are actually seriously considering to adopt wearable devices within their remit. So for example, healthcare is really shifting towards the use of wearable devices to track patients and to monitor their body parameters. And I think you can imagine how this is important at the moment that we are living at. So in a post-pandemic period, where you, for example, want to keep vulnerable patients away from hospitals, so you want to make sure that they are not at risk, but you still want to track, for example, their body parameters, as well as well-being applications and sports that are normally the pioneers, with new technologies that can definitely improve or allow to have a better monitoring of patients. So what we consider wearables at the moment are normally devices that they roughly look like a watch, and you can wear them around your wrist. They can measure 1 or 2 body parameters. They for example, tell you the number of steps or that you have walked over a day. But normally statistics says that around 30% of the people having a new wearable device that looks like a gimmick, they don't use it or dispose of it after, let's say, 3 months. And so this really means that, of course, there's a huge waste if it's thrown away. But also it's not really a device that it's thought to be wearable for a long time and stay with us, simply because it's seen as a new thing, but it's not really reliable. And that's why also there's been a barrier in being adopted in other technologies. So if we look at the concept of wearables, they all share, most of them actually all share a commonality, which is the fact that they look like watches, more or less. Indeed, there are a mix of interconnections and sensors and light-emitting devices, for example, in some cases, but definitely they are far away from what the true meaning of wearable is. So they're not breathable, for example, so you can't keep them on the skin for a long time, and they're neither stretchable, so they don't conform to the skin very well. So that is really a problem, in extending this technology further and being adopted by more serious areas. So what I want to introduce today is an idea of actually considering a new type of wearable technology that, for example, allows us to have devices that are fully conformable to our body. They integrate electronic device and electronic function within it without being limited, for example, by the rigid form factor. So the fact that, of course, we have rigid devices. So try to think about, for example, a wearable glove that actually can teach you how to play piano, or for example, even closer to healthcare application, can improve your posture, or can measure, the position of your body, and it's taking also other devices that are even more intimate in contact with our body and connected to our clothes, like for example, devices that can, of course, inform us in the direction we are taking, also can, for example, identify our presence and can clearly certify, for example, our identity. So devices that through the body parameter actually can directly tell and confirm your identity, as well as as I said before, devices that can enable distance monitoring of body parameters, which is very important for vulnerable patients in for example, in a prospect of a second wave of COVID. And what led me into this, of course, this idea of a new technology, a new really concept for it, is that in the 50s, people were looking at the wearable computer as something that looked like a mini TV, and you can actually wear it like a pair of goggles. And yet, from the 1950s up to 2020, we are not far away, unfortunately, from that idea, because yes, we have wearable devices, or particular devices that are integrated with clothes, but they really normally rely on rigid components still. There is a lot of wiring that is metallic, and definitely there are interconnections at some point. And so these devices are not really washable, wearable, and neither breathable. So there is a key problem there, that if we want to get to something that is fully wearable and yet is an electronic device, or actually an electronic system, we need to fulfill several requirements. Definitely these devices need to be stretchable. So we want really to conform and stretch, ideally following the extension of the skin. They need to be low power devices, particularly if they need to run for a long time without being connected to a battery directly, or using, for example, batteries that don't have a huge storage capacity. They need to be conformable. So the idea of actually really following the skin and following the movement of the body is extremely important in truly wearable devices, like, for example, our clothes do. Clothes crumple, they stretch, but still they're robust. It needs to be breathable. So if we want to wear these devices for a long time, for example, just think about long-time monitoring of ECG or body parameters, we really need to have breathability in order to avoid our skin to actually exchange oxygen and moisture with the outside. They need to be integrated normally with clothes, or ideally made of clothes. So ideally either weavable or integratable, let's say, with with clothes that we wear every day. And on top of that, they need to be washable, also to avoid waste. So one way to actually have sustainable type of electronic device concept is, of course, reusing them. And if you have a clothes that you can't wash or you can't reuse in some cases, because it's not robust enough, unless, of course, it has to be a disposable device, but that's a different story, then, of course, it's a limitation. And on top of that, we need to have sustainable materials. So we need definitely new materials from what I have shown before. We need to move away from the standard rigid electronic chips. And textile is, of course, an ideal material for that, because, of course, we already wear it. So it's definitely wearable. It's actually a highly developed system that allows us, to create clothes, and so to have materials that can conform very well with our body. But of course, we need to have sustainable type of textiles. So looking at, for example, natural fibers or cellulose or materials that anyway are sustainable and biocompatible, it's very important. First of all, because textile in general undergoes washing steps, so everybody knows that. And when you wash a piece of fabric, of course, it undergoes crumpling, it undergoes, of course, absorption of water. So your electronic device that, for example, sits on it or actually is embedded into it will undergo the same processes. So we need to have really robust type of materials together with textiles that allows us to do that. Moreover, textiles are normally functionalized, so they are modified in their function through, for example, a common dyeing process, which is a process that allows pigments or elements to be attached to the fabric. And of course, this is an important step that, for example, it could come to our advantage when we actually want to functionalize electrically our clothes. But of course, we need to deal with these processes because they're industrially relevant, so industry normally uses that. So graphene and 2D materials could be an ideal solution to address some of these properties, and together with other two-dimensional materials, actually could be a platform that could be applied to electronic devices on textiles for wearable applications. So graphene is a single sheet of carbon atoms that is arranged on a honeycomb lattice. And of course, I'm sure most of you know it because it won the Nobel Prize in 2010 at the University of Manchester, but also has been now heavily funded by the European Union in the graphene flagship project. The advantage of it is that actually single graphene sheet is very transparent. So you can try to enable devices that somehow keep transparency, do not vary too much the optical properties. But on the other hand, you can actually use this optical absorption to create electronic devices or optoelectronic devices. It is a conducting material, so you can actually use it as a conducting element, for example, on a textile or on any substrate. You can achieve up to, it can be chemically modified to achieve up to 30 ohm per square sheet resistance. And also it's very stretchable. So the individual graphene crystal unit can be stretched up to 25%. So this, of course, shows that having a stretchable unit allows to have a more conformable type of functional material. And also more recently, there has been a lot of work showing biocompatibility of this material with different type of tissues and cells, starting from skin cells to myocardial cells to actually neuronal cells. So now really there is a good understanding of the biocompatibility of this material that of course drives towards electronic devices that could be in contact with the skin. And the other big advantage is that graphene is not the only single two-dimensional material. It's actually, there is an entire family of layered materials that can be exfoliated to generate 2D materials that have different properties. So this could be, for example, semiconducting with variable properties as a function of the number of layers. They could be wide bandgap semiconductors, so for example, insulators, and you can actually have devices with different dielectric constant and even superconductivity. Some of them also have topological properties. So this becomes extremely important as a platform of new materials that can be used to enable electronic devices on 2D shape. And indeed, this has already been demonstrated. For example, several touchpads have been demonstrated with smart touchpads with graphene on displays or on different substrates, really from wood to textiles. And this enables, of course, versatility of these materials. Also, for example, enhanced haptic devices have been demonstrated with graphene. For example, again, on displays, on smart pads, as well as, for example, on different surfaces, enabling, for example, variation of touches and things like that. And also applications in energy, from batteries to optoelectronic devices. And this, of course, creates really a platform that can be combined together, for example, in healthcare devices or body parameter devices. So for well-being application or healthcare. So this platform is already there because it has already been demonstrated, for example, on flexible substrates. And the way to do that, or one of the best ways to do that, is actually to create inks, because this gives you versatility to actually deposit this functional material on various substrates, particularly for non-conformable substrates, conformable substrates, so non-common substrates. One way that I've explored to do that is actually starting from layered materials and trying to exfoliate these into a liquid or a solvent normally, or it could be also water surfactant dispersions. And by using shear forces or in general power, it is possible to exfoliate layered materials into a so-called graphene ink or an ink of 2D materials. And this can be done in several ways. You can use, for example, ultrasonic exfoliation, shear mixing, or even microfluidization, which is a new material that we have explored more recently and allows to have large-scale production of 2D materials inks. So this works by using a high-pressure chamber where the layered materials are put in on the left-hand side. They go through an intensifier pump and they come out exfoliated. And this is because there is an interaction chamber that essentially generates a turbulent flow. This turbulent flow generates eddy currents, and these eddy currents have very strong shear forces. So you can exfoliate layered materials with a high yield. And this can be actually repeated several times. So with a number of cycles of this repetition, actually you can really create inks in a high production rate, so with a high yield, and particularly with a very good exfoliation. So it is really tunable, so we can control the concentration as well as the flake morphology. So we can actually get the dispersion that we want at the concentration that we want. So this can be nicely seen, for example, by looking at these flakes, starting from the graphite flakes before the microfluidization process, and then going down through different cycles to the exfoliated flakes. So for example, after 100 of these cycles, the microfluidic cycles, it is possible to exfoliate really platelets of graphene or few layers graphene. And this has a very important effect on the electrical properties of the ink. Because with the processing cycles, of course, we change the morphology of our flakes, and this has a strong effect on the sheet resistance, for example, of our flakes. So from this graph, you can see that as the number of processing cycles increases, we have a strong and quick reduction of the sheet resistance. This means that our ink becomes more conducting. So the exfoliation indeed generates a more conducting material because we're actually generating an ink with platelets rather than flakes. So two-dimensionality improves to have thin films with a better electron transfer between the different flakes, therefore a better ink. So this can, for example, go up to conductivities of 10 to the 4th, which is of course pretty relevant for carbon-based inks. But the good thing is that the same process can be applied to a large range of layer and materials, exfoliating them in inks, which then can be used actually to print electronic devices. So these have been already demonstrated, for example, in terms of flexible OLEDs, flexible transistors and touchscreens and so on. But my question is, what if we can use the same process using, for example, printing techniques that are normally relevant in large-scale electronics, like, for example, screen or inkjet printing, and use them on natural fabrics? Can we, for example, enable sustainable e-textile electronics with that? So the question is, of course, whether we can make washable and flexible devices directly on textile. And this can be done certainly by improving the adhesion of these inks of 2D materials on a fabric, particularly on a cotton fabric or natural fabric. So, for example, if we did that, it is possible then to print directly integrated circuits or electronic circuits on fabrics. So for example, you can see here a fully printed touchpad using graphene ink that is interconnected, for example, to a motherboard, and this is also connected to a battery slot and a speaker. So this, for example, can be used as a touchpad in this case, but you can also directly print, for example, radio frequency devices like antennas, which can convert the signal of the touchpad, for example, into an electromagnetic signal that can be transmitted, for example, to a mobile phone or to a Bluetooth device. At the same time, you can also think about other more complex devices like waveguides and so on. And if we want to do that, and we want to make these electronic devices on fabric washable, well, one way to enhance washability that we have explored is actually to start from a natural cotton fabric and use a standard process that is normally used in textile industries for dyeing, which is called cationic modification. So this generates a layer of positive charges on top of the cotton. And of course, these positive charges interact very well for electrostatic bioelectrostatic attraction with negative charges. So if we can take our graphene dispersion, and we oxidize it through a common oxidation process for producing graphene oxide, and then we quench this oxidation through stopping the process with for example H2O2, and then rinsing the graphene oxide, we create an ink which is negatively charged. This of course is oxidized graphene, but has a strong adhesion to our cotton. So then we use this process to create an ink which is negatively charged, and it can be inkjet printed. So here you're looking, for example, at a single droplet generated by an inkjet printing nozzle. And this nozzle generates a droplet with a very precise amount of graphene in it, because the volume is constant. And this is called drop on demand. So you can actually really deterministically deposit your ink wherever you want. With this printing, we can actually create, for example, uniform coatings on cotton fabric. So you can see, for example, on the top, there is a standard cotton fabric image, and the bottom is fully coated with graphene ink. And if we take a cross-section of this fabric, after a hot press reduction, which is normally applied on fabric on textiles, similar, for example, to an ironing process at 120 degrees, you can see that this forms a uniform coating, improves the adhesion of the graphene, and also reduces the top part of our graphene oxide. So the bottom part remains oxidized and adheres very well to the cotton, but the top part becomes reduced. So this goes back and retains or retrieves some of the old properties of the initial graphene ink. One of these, of course, is conductivity. And here, for example, you can see that the adhesion of the film on the left-hand side is very strong. So rather than delaminating from the fabric, it prefers to crack rather than, really coming off. So this, for example, this concept can be actually tailored and controlled to make washable devices. In this case, we achieved washability of up to 20 times. So of course, these addition processes improves the performances, but at the same time, we can make sensors because the cracks on our textiles can be actually linearized and used to monitor, for example, the change in strain, which could be correlated, for example, to uniaxial changes in a position of the wrist, for example. So here you can see a textile-based cotton sensor, which monitors the position of the wrist uniaxially. And actually, in a pretty reliable way, it moves from a very low resistant point to a very high resistance. So this tells us the position of the wrist, and the device can be washed up to 20 times. At the same time, the same concept can be used, for example, to monitor the pressure of, for example, of a piece of cloth. So it can be used as for example, a patch that is attached on top of for example, long sleeve of a jacket within a device. And at the same time, similar type of electrodes can be used to monitor ECG. Now, at the moment, ECG normally uses rigid electrodes made of silver chloride, and around 20% of the patients actually developed irritations due to the interaction of these electrodes with the skin. So what we try to do, we try to essentially compare our graphene electrode with a silver chloride electrode. And the good thing is that we can actually replicate the standard ECG features. For example, these are the PQRST peaks typical of a standard ECG, with a big advantage that the piece of textile or graphene textile is actually stretchable, biocompatible, and also breathable, so it can stay on the skin for a longer time, and you can wash it several times, so potentially can be reused if properly sanitized. And it can operate in ambient conditions. So this becomes very important, for example, to access the 20% of patients that at the moment cannot have, for example, a long ECG monitoring, like a Holter type of monitoring. So of course, these really expand accessibility to monitoring body parameters. Other properties that, of course, were monitored of this coating directly on fabric is, for example, superhydrophobicity. So superhydrophobicity is very important for coatings that, of course, need to withstand, for example, exposure to long time exposure to water. For example, they need to be waterproof or washproof, and at the same time, develop, for example, electrical conductivity. So with graphene coating, in this case, we had a uniform coating by dyeing, by a dyeing process. So by wicking essentially our cotton fabric, which is chemically modified, directly into a graphene ink, we can see, for example, an increase of the conductivity, which corresponds to a decrease of sheet resistance down to 2 kilos. So actually, this is a conducting piece of fabric, which is breathable. We measured up to 1,500 grams meter square per day of a transfer rate, air transfer rate. So this is air permeability. And also we have a very high contact angle. So this contact angle has been monitored after various washing cycles. And the device remains highly waterproof. So this, of course, is very important because as a function of washing cycles, your device keeps working as a waterproof and as an electrically conducting piece of fabric. So for example, these can be used not only as a simple conductor, but for example, we used together with another piece of cotton which is dipped and has been functionalized with boron nitride, which is another wide bandgap insulator two-dimensional material. And we combine these two materials to make a capacitance. So to use it, for example, as a charge storage element. So what we did here, we combined our two graphene fabric electrodes, which are waterproof. In the middle, we put our dielectric boron nitride fabric. And then by applying pressure, we combine this fabric together, creating a three-layer type of textile, which can store energy with a dielectric constant of about 2.4 and can store around 15 nanofarad per centimeter square. So of course, this charged storage element, of course, can be modified as a function of the size, of course, of our piece of fabric of patch. But around, order of around hundreds of nanofarad can already be enough, for example, to power specific type of sensors. So this starts becoming important, for example, for low power sensors that could be directly powered by textile-based storage capacity devices. So then we also tested, for example, the variation as a function of bending. And you can see here that with different bending radius, actually with increasing bending radius, bending radius, there is no change in resistance of the graphene electrodes. And as well as there is a minimum change of the capacitance, achieving less than 1% change in capacitance as a function of strain. So this is a truly example of a biocompatible and sustainable type of fabric using graphene and boron nitride, which are entirely biocompatible type of inks that can be washed and bent and stretched for several times, retaining the original properties. So this really leads towards electronic devices that are entirely textile made with no electronic system, no rigid systems. Then we moved a bit forward. We tried to directly inkjet print electronic devices using different 2D material inks. In this case, we use boron nitride and graphene, where boron nitride is our dielectric and graphene is our channel. And we try to use these inks to make transistors, which are the key element, the single, one of the principal elements of electronics. So we fully print these inks on a cotton fabric. In this case, we have a fabric which is pre-treated with polyurethane in order to reduce the roughness of the fabric. And then we inkjet print these devices, and we can make, for example, electronic components that are fully integrated. So there is no rigid electronics here. We just print boron nitride and graphene into two transistors. We connect them together, and we create a so-called inverter, which is a basic logic circuit that keeps inverting the signal. So you see here, for example, a lot of 1 and 0s. And this is a demonstration that you can actually make, for example, digital electronics fully printed using these inks directly on a piece of textile. So there is no rigid electronics here, you have just a piece of fabric. So this becomes extremely important then if you can wash this for several times. And indeed, here we monitored the washing, the physical and the electrical properties as a function of washing. So you can see here that the electrons and holes mobility, which are key parameters of transistors, do not vary too much. I mean, there is an increase here which we can normally attribute to an initial modification of the properties, but the mobility essentially is the same after several washing cycles and actually remains around 50 centimeters square volt per second after 20 washing cycles. So this means that our transistor keeps working after 20 washing cycles without dramatic changes to its properties. And also, the electrical mobility do not change too much with 4% strain. Here we are at 4% strain with no more than 10% change in the electrical mobility. So this, of course, leads to electronic devices that can withstand the usual processes that our clothes essentially undergo to, and can retain the same physical and electrical properties. However, another important point for truly wearable devices is the biocompatibility. So initially, we start looking at the biocompatibility of our graphene ink on a piece of fabric with different types of cells. We started with neurons, and surprisingly, what we saw is that the neurons not only survive on the graphene textile fabric, but they also try to expand and proliferate, creating proper networks. So this is very important because first of all shows that graphene is actually a good substrate for interaction with skin and biocompatible material, and also is not toxic for those cells, which is extremely important to tackle cytotoxicity, of course, of functional devices. So this leads us to a new concept of biosensors that could be directly integrated on textile. So for example, we can think of arrays of biosensors that could be directly printed on a cotton fabric and actually could exploit the absorption of cotton, leading analytes directly through arrays of multi-control sensors, which are functionalized, for example, with different antibodies, and they can analyze different analytes at the same time. For example, providing multiple readings. So we are now working on this new concept of fully inkjet printed biosensors, which could exploit the same printing arrays of our transistors before, but for example, can monitor different, for example, viral loads. We can look at the viral load of HIV, we can look at the viral load of HPV, and also you can imagine, this is already an ongoing project that we have at the moment, but you can see that this becomes very important, of course, in a pandemic period, of considering other type of viruses. For example, if you can consider a wearable piece of textile that can detect new type of viruses from breathing, for example, this becomes extremely important to, for example, to enhance and help in the track and tracing, for example, of infected patients in the COVID, for example, pandemic. Just imagine a piece of fabric you're wearing or you are actually using on your face mask. So this becomes an extremely interesting technology. It could enable, for example, to different type of devices that could actually be used for remote monitoring. We also moved towards light-emitting devices, for example, towards textile-based displays. And in this case, we use a multi-layer combination of a graphene layer that can be used in this case as a local heater, and then a thermochromic polyurethane. So thermochromic polyurethanes are already biocompatible type of polyurethanes, which are modified with specific thermochromic polymers. These are already used, for example, in textiles. But at the moment, the heaters that are actually enhancing this light switching or color switching are normally enhanced by using, for example, metallic wires or metallic coating. And again, these are not sustainable because they can be washed and they're made of metals that tend to degrade with time. And also it's extremely expensive. So the entire process is not really recyclable and sustainable. So here we're using our graphene coating to provide the same heat and make sure that we can actually convert this different thermochromic polyurethane from one color to the other. And essentially here we showed that we can pattern actually different patterns with our printing process. We can really enable possible displays simply controlled and monitored by applying electrical current through the graphene layer. This, for example, has allowed us not only to demonstrate thermochromic processes, but also to enable different shapes that can be, for example, visualized into a textile-based display directly on a piece of fabric. And these devices are very fast, around 20 milliseconds. But of course, we want to go beyond standard textiles. Textiles are made of fibers. So the principle of actually developing fiber-based electronics has already been explored. The problem is that most of the fiber-based electronics at the moment is done through metallic fibers. And these metallic fibers, of course, are not sustainable, and also they're not biocompatible in most of the cases. But there is a strong need to have biocompatible materials that, for example, can functionalize natural fibers and enable fiber-based electronics. So my idea is actually to move from textile as a substrate to actually fiber-based electronic devices, starting, for example, from cotton or cellulose fibers and functionalizing these with carbon-based electrodes that could, for example, provide some electronic properties. And then these carbon-based electrodes or 2D materials-based electrodes can be woven, can be integrated or knitted directly on a piece of fabric or a textile and impart some specific functionalities. So of course, this new form factor enables also a new type of electronics. So the idea is to use materials like polymers, also carbon-based materials, together with, for example, sensing materials like nanomaterials, to create fiber-based electronic components, which could be, for example, individually providing specific optoelectronic properties, like, I don't know, light-emitting fibers, or for example, light detection fibers, or transistor fibers, that can be woven together and integrated into a fiber-based electronics form factor. So this concept has already been explored, but none of these fibers actually at the moment are entirely made of biocompatible natural components. So I'm exploring different type of fiber-based manufacturing processes. For example, extrusion and spinning is one of those, mostly looking at, for example, melt spinning processes or extrusion, but also wet spinning is very important. For low concentration fibers, they could have more conformable type of form factor. And then these fibers can, for example, be integrated together or yarned to create functional fibers by making sure that two different fibers can interact together. So what I'm doing at the moment, I'm actually using cotton or cellulose starting elements, and I'm mixing them together with my graphene ink to actually spin out graphene cotton fibers or graphene cellulose fibers with a high loading of graphene. And then these fibers can be yarned together, for example, they can be dried, providing a very neat type of fibers which are electrically conducting and can be used, for example, not only to, of course, impart electrical conductivity, but actually also to conduct heat. So they can have multiple functions, for example, in thermal monitoring or thermal management, as well as electronic devices. So at the moment, we're exploring various types of fibers production. For example, we're using graphene oxide dispersions, and these dispersions can be wet spun into a kind of rotating bath. Now, normally, properly tailored graphene oxide dispersions have a high loading of graphene. For example, you can see from the image, there's a large loading of very large flakes. So this can be, for example, spun out from a wet spinning process, and then they can be coagulated into fiber. And these fibers, because of the flakes are very large, then can be reduced into reduced graphene oxide and can show very robust properties. For example, you can see here they can be knocked together into a robust fiber. They can also be used for knitting. So you can combine these fibers into a yarn and you can knit them or even weave them together. So this becomes extremely important to have electronic devices on the fiber. At the moment, these, of course, don't have active electronic properties. They are normally electrical conductors or thermal conductors. But what I'm trying to do at the moment, I'm trying to use these graphene fibers and use, for example, them as electrodes together with other 2D material inks like boron nitride or molybdenum disulfide, which is for the molybdenum diselenide, which are semiconductors, and create fiber-based electronic devices. So you can think, for example, of a fiber-based transistor or a fiber-based photovoltaic device. And these devices, of course, will enhance the properties of a single graphene fibers, for example, enabling to do logic electronics or logic gates directly on a piece of fabric, or for example, detect light or generate energy from the sun, or even be used as energy storage. For example, this can be done in solar cells at the moment, and we're exploring tuning of the energy gaps in this specific case, the energy levels, sorry, in this specific case, to make sure that we can actually enhance the efficiency of the solar cell and the fiber. The way to do that is to start from our graphene fiber and then functionalize it, for example, with some polymers like P.PSS. So these polymers, of course, have various functional properties. First of all, being a polymer makes sure that our fiber is pretty smooth. And second, can change the energy function, the work function. So it is possible, for example, to shift the Fermi level and enhance, for example, electrons hopping between the graphene to another layer that could be coated on top of it. And indeed, that's exactly what we do. After coating the graphene fiber with a P.PSS, we actually use a semiconducting layer, which is made of a MOS2 coating. So this MOS2 coating is a semiconducting layer. Here you can see a chemical analysis from EDX on the fiber, where we can actually see the molybdenum and the sulfur, which is uniformly coating our fiber. And this, of course, allows to have a semiconducting layer that, for example, can generate electrons hopping. And this allows to have, for example, photodetectors or even transistors. So for example, if we want to make a photodetector, what we try to do, we try to use the semiconducting layer in the middle, and then we collect the electrons that are generated, for example, from the semiconducting material via two electrodes. On one side, we have our graphene electrode, and on the other hand, we put a silver electrode, silver nanowires electrode. Now, silver is known to be another biocompatible material, so again, it fits within the framework of having a totally biocompatible fiber. So here you can see the cross-section of the fiber, and if we look closer to the edges, we actually see our graphene fiber, so this is the cross-section of it, and then we have this thin layer, which is actually the active layer of our fiber. So here you can see that this section here is made of the silver, which is our external electrode, then the MOS2, which is our semiconducting fiber, and then we have a layer of graphene and P.PSS, which is the other coating that I showed you before. And the good thing is that this device which is entirely made of fibers. There is no rigid electronics here. It's again graphene, cotton, and other 2D materials. Actually acts as a very efficient fiber-based photodetector with a switching time of around 140 milliseconds, and it operates at different wavelengths. So for example, this really shows that the entire new platform based on 2D materials and fibers can be used to make electronic devices and optoelectronic devices. So my vision for this is that really in a short term, let's say 5 years, this can really lead, for example, to fabrics that are fully functional electrically and also optoelectronically. You can make, for example, light emitting fabric displays and also sensors. So you can make, for example, less use of screens, rigid screens or flexible screens, and can actually make more integrated type of textiles that replace screens. And of course, if some of these could be, for example, sustainable or natural, becomes actually extremely important to reduce waste of electronics. At the same time, FIRST has a huge impact on, for example, body area networks of distributed sensors on, for example, pieces of textiles. It could be applied also to wearable power generators. I didn't touch that side, but of course, most of these inks could be used also as energy storage or also energy generators on a fabric. And on a longer term, of course, this type of fibers could be also used directly in contact with biological tissues, enabling the concept of bioelectronics. For example, by creating fiber-based electrodes that are directly in contact with our living electrodes, like for example, neurons, and trying to essentially mimic an artificial type of neuronal network, which is totally biocompatible and can directly talk, for example, with neurons. This is already an ongoing project that we have together with other collaborators on, for example, using fiber-based device that could regenerate specific tissues, like, for example, spinal cord or even brain tissues. And then with this, I would like to thank you very much. And also I would like to acknowledge all the funding agency for funding this work. I can see that there are a lot of questions here. Well, actually, there's 3 questions. So one question says, what kind of fabric is this? Is there any specific need of fabric? As there are many types, and these are these commercially sourced. So the fabric that we use is a standard cotton fabric. So this was supplied by collaborators that we work with. Some of those papers actually were published with groups that are textile manufacturers, essentially. So they can spin out or they can create cotton textiles. So they buy essentially the cotton fibers and they weave them together or knit them together. So these are standard cotton fibers from standard cotton suppliers. Some of them come from US cotton. Some others come, for example, from Indian cotton. There is different type of sources, or China, for example, but these are standard cotton fibers. So the good thing is that the modification that I showed, this cationic modification, is actually done directly on the fiber, on the cotton fiber. So it directly acts on the surface of the fibers and improves the adhesion of the 2D materials. A second question is about, with neurons on graphene base, can you record electrical activity? The answer is yes. This has already been shown. There is an ACS nano paper back in 2016, and following on from that, there's been actually a lot of work on graphene interfaces for monitoring neuronal activity. For example, well, in different types of cells, you can monitor activation energy, but in neurons, actually, you can look at the synaptic transport and the neuronal activity. So definitely, yes, there is, we have a project on that already, but there is definitely a clear evidence that you can use these electrodes for that. Amazing work and talk for each other. Thank you very much. Do you think it's possible to use graphene and other 2D materials to create topological insulating or thermal electrical conducting fibers? So definitely to create topological insulators, yes, absolutely. I mean, there is a lot of examples of 2D materials for topological insulators. The big question is whether you can retain the topology on a fiber. Of course, having a different form factor, this could have an impact, of course, on the topology and therefore on the surface properties of 2D materials, because most of the topological insulators, of course, have surface properties that are different from the bulk properties. On 2D materials, of course, it might be more possible because, of course, the surface properties will be maximized, essentially being an entirely 2D material. So I think it might be very interesting. However, I definitely think it's also very challenging because retaining topological properties of a fiber is challenging, but I think we can talk more about it if you are interested, Jonathan. And yeah, there's one more question. Are the experiments done with detection of chemical levels in body fluids such as sweat? i.e., are the current research for this wearable to be used as monitoring devices for diabetic patients? This is a very good question. Of course, there is a lot of interest in glucose monitoring, for example, for diabetic patients. The problem is that the concentration of glucose, as far as I'm aware, on sweat is very low. So normally it's actually very challenging to achieve the right sensitivity to monitor glucose directly from sweat. And I'm not aware of, well, definitely these devices could have improved sensitivity because they are three-dimensional devices. Every electrode is actually a very porous type of electrode. So of course you can think of these devices as a highly porous and high surface area electrodes. So this has a very beneficial effect on the sensitivity of the electrodes. But on the other hand, I have no idea whether we are beyond, the sensitivity thresholds that we need for glucose sensors at this stage. But definitely, there is interest for using this type of technology for sensors as an interstitial fluid type of sensor. So fluids that, for example, use microneedles that can penetrate the external layer of the skin and can actually extract interstitial fluids which have a higher concentration of glucose. And in that case, I think there could be a much larger interest in, because of course we'll have a high concentration, so we might be closer to the right sensitivity for that. There is another question. You mentioned the issue of cost for metal conductors. How is the cost of graphene ink in comparison? And is the manufacturer scalable to reduce price of mass production? So definitely, when I say metal, if you want to have metals that are washable, you can't use standard metal wires. So you need to use wires that, for example, are made of stainless steel, or it could be treated silver or gold, even gold. So of course, these metals are very expensive. You can think of for example, I think a liter of silver ink costs around 2,000, above 2,000 pounds. Of course, it depends on the concentration and the quality of the silver, if it's silver nanowires or silver nanoparticles. But we're looking at something like that. A liter of graphene ink with a concentration of around 10 milligrams per milliliter is not going to cost more than 500, maybe 700 pounds. So definitely there is an order of magnitude roughly of change. Of course, it depends on the quality of the graphene ink. In this case, actually, you don't even need high quality inks unless you want to make transistors. And in that case, of course, you might need a high performing type of ink, for example, with a high loading of 2D materials, so single atomic sheets of graphene. But if you're interested in electrodes, you can really live with less performing type of inks, which are still very good for electrodes. There is another question. Why do you think it takes around 20 years to apply your technology to bioelectronics, while there are many applications in 5 years? What is the most difficult point for that? Well, most of the applications in bioelectronics normally need long-term monitoring. So the long-term monitoring, I think, is a key point to be addressed there. So the ability to fully incorporate these devices, for example, for a long term in our body. And of course, there is a huge interest in addressing this point, enabling, for example, devices that could go beyond the short-term immediate monitoring, for example, of specific body tissues, and actually be implanted and stay there for a long time without affecting the electrical performances, the sensing performances, as well as, of course, without causing any inflammatory response from the tissue. And I think this is a key point that needs to be tackled together, of course, with the sensitivity of this type of devices. So of course, there is a huge interest in this, and this is a key area that needs to be tackled. So that's why I'm saying that it might take longer, but definitely there could be disruptive changes even in the next 5 years. I'm not saying that in the next 5 years you can't have devices that could be implanted for long term, but if you want to have fully bioelectronic based devices for long-term implantation, it might take longer. There is another question from Mustafa. With neurons on a graphene base, can you record? Yes, I already answered this, and yes, there's been a lot of work already on this, and there is evidences that this can be, the electrical activity can be monitored. Right. So I think there is no more questions. Maybe there's one more.
There was just one more question. Sorry.
Yeah. What about the use of silver in the textile industry? There is severely limited due to its dissolution and harmful effect on the environment. That, yes, correct. That's another very good point. Despite silver being actually biocompatible, it is an environmental concern. So actually using carbon-based electrodes, which are definitely more compatible with the environment. I mean, graphene, normally we synthesize graphene from graphite, which is actually coming from natural mines. So from this point of view, we have really a direct use of a natural source of that can be essentially recycled and reused, and eventually could be disposed. Particularly if you are considering that cellulose-based fibers are again made of carbon, so the entire electrode would be essentially a carbon-based element. So from this point of view, I think definitely using carbon-based electrodes with very good performances that can be offered by graphene is a way to tackle the harmful effects of silver electrodes. There is, so is there any work done on recycling graphene from cellulose? So there are recent works, yes, on recycling graphene. So for example, reusing graphene by detaching, by essentially separating the graphene from the cellulose via various centrifugation steps, and then recycling the graphene as a new graphene ink. Of course, the good thing is that cellulose can disperse graphene very well. So essentially, if you dilute or if you dissolve cellulose, what happens is that the cellulose itself can stabilize graphene in a solvent. So by using essentially specific solvents that can dissolve graphene, this can redisperse the graphene in a graphene ink that you can reuse. So definitely there is a lot of course, unless the cellulose is heavily cross-linked, then it becomes difficult to dissolve. But yes, there are. Compared to the Maxins, it seems better, isn't it? Well, it depends. Better or worse, it really depends. Because Maxins are, I think the concept of better or worse, it really depends. Better than Maxins, it could be, it depends whether you're looking at cost or performances or platform. Maxins are a very large family that has been used already in textiles, but most of the applications of graphene have been explored at the moment in the area of energy storage, where electrodes are actually used as a high surface energy electrodes. Electrodes. And in that case, actually, Maxins has shown even more promising properties than graphene. But because Maxins do not come with a large range of other 2D materials that the platform that I've shown proposes, for example, at the state of the art, with the state of the art, it's impossible to make, for example, electronic devices that are active, so photodetectors or transistors with Maxins. Plus, the synthesis of Maxins is not sustainable. So that's why in my talk, I didn't mention Maxins, because I focus on the sustainability of the process. And at the moment, Maxins are synthesized with a not really sustainable process that uses very harsh chemicals. Is there any, is there any problem with the nanoparticle toxicity with graphene nanoplatelets? There's been a lot of work on within the graphene flagship and also outside the flagship, I would say over the last 5 years now, clearly showing that at least with graphene, there is a clear understanding that pristine graphene and low chemically graphene oxide or reduced graphene oxide with very low chemical modification is not harmful. Most of the harmfulness of the carbon-based materials comes from their form factor and comes from the fact that, of course, they are hard to be either expelled or by the body, or they actually penetrate the cell because of their natural form factor. So large form factor graphene flakes that, for example, are the case of these fibers, where you can make very robust fibers to make, for example, graphene fibers. They have been shown to be actually highly biocompatible. Plus, there are a lot of recent studies, I think from 2018 onwards, within the work package of biocompatibility of the graphene flagship, clearly showing that the cytotoxicity levels of graphene, reduced graphene oxide films is actually extremely, extremely low.